Well, let's look at the spin orbit. We know the eigen values are the matrix elements. Of the spin orbit interaction in the coupled representation. And that is equal to a half times the expectation value of the radial part, which is 1 over r cubed. That's that 1 over r d by dr term. And then the expectation value of L dot S, which we have written over there, which is j plus 1 minus L plus 1 minus 3/4 over 2. So this is the matrix element of this operator. Thank you. So we need to evaluate this. This is equal to 1 over n cubed. We did this for homework. So, putting this all together, we get the following. Putting back in alpha squared, the expectation value here is equal to alpha squared over 4 n cubed L plus 1 times L plus a half times L if j is equal to L plus a half and minus L plus 1 if j is equal to L minus a half. Okay? So that's just plugging in here the two possible values of j. The j can in hydrogen can either be L plus a half or L minus a half. In the case of L equals 2, you can calculate what it is. Let's complete this. For the 2p3 halves, the shift is alpha squared over 96. For the 2p1 half, the spin orbit shift is minus alpha squared over 8. And of course, for the 2s, there is no spin orbit coupling, since L equals 0. So, what do we see? Let's just write down a spectrum. In the absence of relativistic effects, we had an 8-dimensional n equals 2 manifold of sublevels. The 2 different 2s states, the 6 different 2p states. If we add in just the spin orbit alone, what this shift tells us is that we have new good quantum numbers. Now, instead of m sub l's and m sub s's, we have j's and m sub j's. We have 4-fold degenerate here, 2-fold degenerate here, 2-fold degenerate here. 8 states. This is with spin orbit. But now we also have we add back in the Darwin term and the relativistic kinetic energy term to get the total relativistic correction. And what do we get? When you put that all together, you find the following. These guys come back together. The 2s 1/2 and the 2p 1/2 are down here, and then the 2p 3/2 is up here. So this, let's see. This guy, this should be degenerate. The 2s shifted down due to the combination of the relativistic kinetic energy term and the Darwin effect. Both the 2p 3/2 and 2p 1/2 also get a relativistic kinetic energy shift. And we get degeneracy again. Why? Well, the reason here, what we see is that the energy depends only on J, as it must, because the total angular momentum of the electron is conserved here. We had our spherical symmetry, and we had the Dirac equation. And in fact, the Dirac equation gives us the following energy levels. They only depend on J. This is the expression that you get from doing perturbation theory on the Dirac equation to lowest order in the fine structure constant. What you see here is this is the rest mass energy, this is the usual Coulomb energy, and this energy is the correction term. This correction term is, in fact, only dependent on J, not L. So, in hydrogen, what we have is still a degeneracy in J. This splitting is known as the fine structure splitting. And that splitting is, what is it? How big is it? About 11 gigahertz. Now, final point before we break. In fact, as we discussed, there is something missing from this description in terms of the relativistic corrections due to quantum electromagnetic field. If I include the effect of vacuum fluctuations, then I break some of this degeneracy. And what one finds is that the n equals 2 spectrum looks something like this. The 2s and 2p states are no longer degenerate. They depend on the total angular momentum, including the photon angular momentum. But they don't. It's not but it does. It's not the same for states with the same L as it was in Amsterdam. And this shift here is known as the Lamb shift. And the Lamb shift, I should know off the top of my head, but I don't remember. So let's see what I got here in my notes. Yeah. So the Lamb shift is on the order of a megahertz. It's tiny compared to this splitting, which is thousands of times bigger than this. But it's a full spectrum, including everything other than the nuclear spin effect, which we still didn't get to, but we'll get to next time. But this is the story of fine structure. So we will have a lecture on Friday. I'll review what I went through very rapidly at the end here. The notes are posted. And I do urge you to review questions about the addition of angular moment and the Clebsch order coefficients. So we'll break for now.